Good evening, everyone, and welcome at our 2020 Incentive Awardee lecture entitled The Rising of Metal-Oxo Cluster-Based Catalysts for the Formation of Amide Bonds by Dr. Francisco Azambuja. These webinars are organized by the KVCV, or the Royal Flemish Chemical Society, of which I'm going to give you now a short introduction. The KVCV is the chemical society within Flanders, so the northern, the Dutch-speaking part of Belgium. We are a community of chemists in Flanders and far beyond, because everyone can become a member of our society. And our members are mainly students, PhD students, academics, teachers, and professionals. So we really do represent and strive to support everyone within the chemical education, industry, and society. We mainly organize lectures about popular scientific topics for a general audience or more domain-specific workshops. Normally, after our events, we have a networking reception, but unfortunately, in the digital editions, this is not possible. Here you have an overview of our upcoming events. If you want to have any more information or for registration, you can always visit our website, kvcv.be/calendar. Mens en Moleculen is our magazine, which is in Dutch, and is distributed to all our members each month. So this means we have 12 editions a year. And in this magazine, you can find news about the chemical industry, but also academics, our own activities, and some scientific advancement, and much more. If you are a member of KVCV, you're automatically also a member of UNICAMP, European Chemical Society. And as a member of UNICAMP, you have discount at various activities endorsed by UNICAMP. If you are a member of the KVCV, we have reduced prices at our activities. You also receive, as already mentioned, our magazine Mens en Moleculen, but you're also part of the scientific chemistry community, which helps you to extend your knowledge and broaden your network. For a PhD student, for example, it's only 12 euros a year to become a member. If you are interested, I recommend you to visit our website, kvcv.be/membership. So let's stay in touch. If you need any more information, you can always visit our website, kvcv.be, or we can also be reached via our social media channels. We have a Facebook page, but also a YouTube channel on which you can rewatch all our webinars again. And we also have a LinkedIn page. This series of webinars is supported by Chemistry Europe, so you can always have a look at their journals, as they might be of interest for your next publications. And now I will give the word to Robert Schoonheid, who will host this webinar. So Robert, I will give the screen to you.
Okay, thank you. I am Robert Schoonheid. I'm president of the CGB-CBB, and that's the CGB stands for Comité Gestion du Bulletin, and CBB stands for Comité van Beheer van dit Bulletin. It's a small organization which is established 25 years ago as a intermediate between the Belgian chemical societies, de Société Royale de Chemie en Koninklijke Vlaamse Chemische Vereniging. And CGB-CBB is an intermediate between the European Chemistry Europe and our chemical societies. Chemistry Europe, which is a new name for what was formerly ChemPub journals. These journals are published by Wiley, and some of the profit of Wiley goes back to the chemical societies. We manage the money that goes to the chemical societies in Belgium. So here you see some of the journals that are published by Chemistry Europe, and for which we get some financial support. This financial support is mainly based on the number of publications of Belgian scientists in these journals. So the more you publish in the journals, the more money we receive, and this money goes partly to the chemical societies. Other part of the money is we use for travel grants, for organization of international conferences, and for incentive awards. You see them all three here, and you can apply to CGB, CBB to get travel grants. That's typically for PhD students. Incentive awards is typically for postdocs, and international conferences are for the organizing committee. So the incentive awards is given every year to maximum 2 Belgian scientists who do research in Belgian laboratories. And this year we had, or in 2020 at least, we had 2 applications, and we choose as a winner. One of these winners is Dr. Francisco de Azambuja, and you see here that the price that he receives is 2,500 euros. So Dr. Azambuja is originated from Brazil, and he did his studies and his research in Brazil, in the USA, in Germany, and presently is in the lab of Professor Tatjana Voogd-Barak in Belgium at the KU Leuven, and his research is concerned with the combination of organic chemistry with catalysis by metal ions and polyoxide metalates. He's also an expert in fluorine chemistry, and he has very long experience in several research laboratories all over the world, as I said, Brazil, USA, Germany, and now Belgium. So I think it's now, I give the word to Dr. Azambuja to present this incentive award. Thank you.
Hello. Yeah. Okay. Thank you. Thank you, Professor Robert, for the kind introduction. Good evening, everyone. From my side, I would like to start by thanking the KVCV for this kind invitation, and also the Belgian community that through CGB and CVB for considering me for this incentive award. I think among all the things that I planned when I arrived in Belgium 2 years ago, I would never imagine that today I would be here as the receiver of this award and talking to you. And for me, this is a very special occasion. I would like, before anything, to dedicate this award to my wonderful friends and colleagues at the Bioinorganic chemistry team at KU Leuven. That has helped me a lot since I arrived. For me, they are the real winners of this award, because without their help and dedication, I would not be standing here today talking to you. Of course, I'm deeply honored to receiving this distinction from a prestigious community such as the Belgian one. And I'm very grateful to everyone that helped me along the way. I hope that that I will fulfill the expectations of this award as being an incentive, and be able to come back in a couple of years and talk more about some great science that hopefully I'll be able to keep doing. Considering this is an award lecture from concerning my career, I thought I would start with the 2 bits about myself before jumping into the chemistry that I promised to talk about today. As you realized, and as already told, I'm not from Belgium. I was actually born and raised in the south of Brazil. And then around my 20s, I moved to Campinas, which is a city close to São Paulo, or biggest city in Brazil, to conduct my studies at UNICAMP, which is my alma mater. So I spent there around 10 years from my bachelor's all through my PhD, except for a 1-year internship in the lab of Professor Glores in Germany. And for a big part of my time, I worked with a very straightforward chemistry that is here on the right side of the slide, the Heck-Matsuda reaction. When I finished my education in Brazil, I moved to US because having a 1-year time in Germany already during my PhD, I wanted to experience the research environment somewhere else. So this is how I end up in the medicinal chemistry department of the University of Kansas, working with fluoroalkylation reactions in the group of Professor Altman's that is now at the Purdue University. And there, among several things that I was involved with, I mainly developed these 2 projects that I show here, building on some previous results of former colleagues there. And the first one is mainly involves the converting these readily available alcohols directly into trifluoromethyl compounds in a single step. And to make a long story short, the way we came around with this to achieve this was to develop this new trifluoromethylation reagent, which with some assistance of catalytic copper would be converting the initial alcohols to trifluoromethyl compounds. And this method circumvents, let's say, a more traditional strategy where this alcohol has first to be derivatized before installation of the CF3 moiety. And then even the product of this step has also to be further worked on the synthesis until you get the final compound. The second project was a little bit more complex than that, but it also gave access, streamlined the access to fluoroalkylated aromatics through this remote para-CH functionalization that was actually very selective. And it was quite interesting, this reaction, because we only needed palladium tetrakis triphenylphosphine as a catalyst instead of some fancy catalytic system or any chelational system, as is usually needed when you want to access such a remote bond like that. What actually did the trick for us was the triethylamine that provided re-aromatized this de-aromatized intermediate that was actually there, and very few people were aware that it was there. And I think this is very cool because not many reactions you can achieve this level of selectivity without more complex ligand systems that would be required for cross-coupling reactions or CH activation reactions that would be a more conventional way to accessing these substrates. For us, what actually did the trick was a simple, readily available base like triethylamine. So these 2 projects, they were important for me because they made me reevaluate a little bit my thoughts about which kind of reactions and how do we develop reactions in the lab. First, because made me realize how complicated a few reactions still are. One would argue, I think, that the main benefit of these 2 projects that I developed there is that it is streamlined the access to key building blocks in just a single step that would take other chemists a lot more steps to achieve the same transformations. And I think that's ended up being a very relevant aspect because this also influences a lot to which extent these methods will be viable in a more real-world kind of application, so to say. The second aspect, and probably even more relevant than that, is that how much these 2 innovations that we developed there at the time were linked to the fundamental chemistry, to the fundamental reactivity of the species that were involved in these reactions, and how understanding that allowed us to access more simplified, more simple synthetic methods. So with these ideas in mind, that's when I came to Belgium to work with in the bioinorganic chemistry lab at KU Leuven. And when I arrived here, the main line of work, I would say, was, and maybe it still is, the development of Metal-Oxo cluster artificial proteases that using catalysts like these ones that I show here, the peptide bonds in substrates as complicated as proteins would be cleaved in a very smooth way. So the Metal-Oxo clusters I didn't know at the time, but they are actually a huge group of molecules with different classes, let's say, of clusters that you can have out there. And here in Leuven, we mainly use the polyoxometalates, which are intrinsically anionic compounds. Here I'm only showing the cluster, but there's a lot of cations involved here as well. Also some oxo clusters, which tend to be neutral compounds as you equilibrate the charges with some capping ligands. And also these discrete oxo clusters in different shapes and forms can be embedded in these three-dimensional materials, such as the metal-organic frameworks. So for my work here, I will focus only on mainly on the polyoxometalates and talk a little bit about the MOFs at the end. But this hydrolytic work, I think it's a truly fascinating work with many lessons for catalysis. And if you are a little bit curious about it, I would encourage that you go and take a look on this account that appeared online a few days ago to get more details about it. So talking about POMs, that will be my main class of catalysts in this talk. What are they about? I think they are actually a very interesting class of compounds because you can essentially make them from very simple inorganic salts and ions under not so complicated, usually aqueous conditions that provide you with these well-defined structures. And here I'm showing as a representative example the synthesis of phosphotungstate POMs, starting from these two ions or given here a structure that we call a Wells-Dowson POM. This is the ballistic model, but we also represent this usually with the polyhedral view because it's, I think, a little bit easier to realize what is going on around here. But the composition of these compounds and the shapes can be varied on a lot of different structures that are already described out there in the literature. And it's not only what you cook and then what you get the product that you can use, you can actually manipulate these structures by changing the conditions of the solution. Usually, we change a little bit of the pH on aqueous solutions to create vacancies on these planary structures. And on this vacancy, you actually have 4 oxygens. They're ready to receive, to be stabilized further by cations. So they have a strong affinity for positive metal ions that when we add metal salts to the solution, complexing and forming these metal substituted polyoxometalates or metal complexes, as I like to call them. And then by adding an appropriate cation, you can selectively precipitate these compounds. And a lot of structures have already been reported in the literature. I just show here a few of the phosphotungstates that the group in Leuven has worked with in the past few years. And I think it's also interesting that it's not only the POM structure that can change from Wells-Dowson to the Keggin or to the Lindquist, but also the ratio between the metal and POM ligands that you can have on these compounds. Also giving them, again, not only what you can get from the solution, but also an opportunity to design these compounds and these catalysts to whatever application you are thinking about. So when I arrived to Leuven, what actually got my attention was what made me cross from the organic to the inorganic side of chemistry was this reaction that I show here on this slide. The hydrolysis of the glycylglycine, or Gly-Gly as we call in the lab, in the presence of zirconium bonds affording glycine, was published by the group early in 2012. And frankly, as coming from the organic chemistry experience that I had previously over my education, this was nothing impressive in terms of organic reaction. This reaction at first, I mean, it's too long, 50,000 minutes, it's around a 1 month reaction for doing something that probably you can do a very similar thing with a basic or an acidic solution. So this reactivity actually makes a lot of sense for a lot more of the other substrates that the group has been using, including the more complex proteins. But for simply hydrolyzing Gly-Gly from a purely organic chemistry perspective, I think that that was still not really clear what would be the point of it. But even if you are critical at this point, I think once you start looking more to this system, you start to realize that some interesting features are present in this system. First, I was impressed by how resilient the loose acidity of these metal-POM complexes were for these reactions in water. And second, as I just showed you, these zirconium bonds that were used at the time, they are quite inexpensive and readily available compounds, and very robust as well, which is what do you want for any catalyst to start with. But what really caught my attention in this reaction was not exactly this part of transformation, but this minor product that was being observed in the early stages of the reaction. This minor product that appeared and then faded away as the reaction went for a longer time. Further work on this actually showed that what was being formed was the cyclized dipeptide, which was actually very opposite of what they were doing, they were trying to do in the hydrolysis of Gly-Gly. But this is, if you look into this, this is instead of hydrolysis and amide bond formation that was happening in water. Even if it was observed in Leuven, this gave me a hint that something else could be going on out there. And what they did conclude in the end after the initial studies that this cyclized structure was actually in equilibrium with the open one, and the open one was the one being hydrolyzed. So the reason I was intrigued by this is because if you go back to the fundamentals of this reaction and you look to the mechanism and the intermediates that are involved in this reaction, you realize that these intermediates that lead to the hydrolysis of the product are the same intermediates that are used on the formation of the peptide bond. And I think this is a very interesting feature of the system, because if you can get the catalyst to work on the other direction, you might have an interesting system for forming amide bonds. And I think this brings me back to the point where simplifying reactions is an important goal, especially nowadays where you've got the sustainability and the environmental requirements for new reactions that have to be developed. But if you think on the amide bond, it's a very basic organic transformation in testable chemistry. So what would be important all about that? And I have to say, when I started studying this subject, I was a little bit surprised myself on how much we still depend on the amide bond formation, and how better we can still be in this area. So let me show you why the amide bonds are still important. I think they are relevant in a number of industrial and academic settings. But just to share a more concrete data, I show you here this chart that was published a few years ago in the Journal of Medicinal Chemistry, comparing the medicinal chemistry reactions used in 1984 close to when I was born, actually, and to 2014, so 30 years later. And you can see that amide bond was, and it still is, one of the most frequent reactions that are used in medicinal chemistry in general for synthesizing drug candidates. So even though, let's say, more famous couplings like the cross couplings are at the very end of this reaction, they are quite useful for medicinal chemists, the amide bond is still there, and it's still necessary that we do it very well. And because it's so frequently, you would think that, well, now we master the synthesis of amide bonds, but I have to say that this is not really the case as well. Because one of the main methods, and actually it's a very powerful set of reactions to synthesize the amide bonds, is that when you take the carboxylic acid, which is obviously the obvious starting material for these reactions, and you want to react directly with the amine, not always this reaction happens. So using amide coupling reagents, you activate this carboxylic acid, making it more more prone to be attacked by the amine, forming the amide bond. And this would be very okay if you wouldn't generate also a stoichiometric or a super stoichiometric amount of waste to make this chemistry happen. Let's make this more concrete. I went down to the literature and just picked one random coupling using this traditional approach that is used both in academia and industry as well. And I highlighted here in blue the carbons that would be incorporated in the final product, a glycine tryptophan dipeptide there. And you can use different metrics or different parameters to look into it, either on the molecular weight of the blue part that will be incorporated in the final product, or the molecular weight of the protecting group that we have to use to make this reaction work. Or you can count a number of carbons, and you realize that as efficient as this reaction is, there's a lot of carbons and mass that will not be incorporated in the final product. Actually, here I even went ahead and calculated using only these two reagents, so not counting the solvent, what would you need to produce 1 millimole of this final dipeptide? And actually you would need 17 times more mass of reagents to get only a tiny amount of the product. While this is not a big problem in a vial in the hood, in the lab, or in the research condition, for if you scale this up, it starts to be really inconvenient. So I think these methods, the amide coupling reagents, they are very powerful, but I think we all agree that we need to start thinking of how can we do better in these transformations. So there's a lot of different methods for doing amide bonds, but I think what I preach is what I learned from this review that came out a few years ago, mentioning that the direct amide bond formation is actually one of the best reactions to go. If you could mix directly the free non-activated carboxylic acid and just a simple amine, getting the final amide product, only water would be formed as the byproduct. And this is as good as you can get starting from these two starting materials that are also readily available. But the problem is that when you mix an acid and a base, I mean, you have the direct formation or the quick formation of this stable salt, that to deproportionate this ionic pair into the amide bond, you would need quite high temperatures, estimated in around 160 Celsius or even higher. And as you probably know very well, it's not every substrate that can handle these kind of temperatures. And that's where catalysis will play a role on bringing this temperature down and streamlining this process. Of course, I'm not the first one to approach this problem on from looking for a new catalyst, and a couple of catalysts are listed here from all of those that have been devised in the literature. But I would say that very common are these group 4 metal salts and group 5 metal salts. And there is also, I think, since the last 30 years, a lot of boron compounds have been shown quite some activity on this reaction. The catch for the systems that are getting actually very decent reactions out there is the conditions in which these reactions have to be conducted. Most of them still need some inert reaction conditions and even dry solvents to afford good yields of the final amide product. And most importantly, the water scavenger needs to be used so that the water is removed and thermodynamically the equilibrium is shifted towards the formation of the amide product. So this seems like simple things to solve with, but these drawbacks on the reaction conditions for these quite efficient catalysts hamper the transfer of these catalytic methods for larger scale synthesis in the industry. So in this big parenthesis that I did talking about the synthesis of the current state of the art for the synthesis of amides, you start to realize that maybe something more interesting is present on this reaction that the group in Leuven reported early 2012. If you could transform this and favor the cyclization over the hydrolysis by designing new reaction conditions, this would probably lead to a much better catalytic process for the formation of amides. So when we started this, I mean, there were open questions. I mean, would you need some additive to activate these carboxylic acids and make it reactive enough, given the robustness of these metal-POM complexes? Would it be some sort of water tolerant, and could you even recycle these systems? And also, we didn't know if these systems would be homogeneous or heterogeneous to start with, as the metal-POMs complexes are usually soluble in water. So with this scenario and this perspective ahead of us, the first thing that we did was to go back and reanalyze this reaction that the group has looked into it before, evaluating this for what it actually is, that it's an equilibrium between these three species, the cyclized, the open Gly-Gly, and the hydrolyzed product, the glycine. And what this equilibrium tells you is that essentially if you remove water, you come to the right on this equilibrium. And if you add water, you are going to the left toward the hydrolyzed product. So as we needed to eliminate water, the first thing that we did was to screen a bunch of organic solvents to visualize where this wood equilibrium stands in the presence of these zirconium-POM catalysts. And for a lot of solvents, we basically didn't observe anything. The system just sit still on the Gly-Gly point and didn't move. But for DMSO, we got quite a nice reactivity where 50% of our desired product was formed after 24 hours of reaction. And I think most importantly, no hydrolysis was observed, showing that the system could be quite selective. So this was, for me, a very good day in the lab where I could learn that the systems would actually work in the way that we predicted. And so I moved on with the optimization of these reactions. And we quickly learned that hafnium and zirconium were quite unique catalyst metals that would provide the catalytic activity we were expecting. Using these model metal-POM compounds as references, other first-row transition metals were not actually catalytic active, and even some serine compounds that showed reactivity under the hydrolysis conditions were not active at all. More, I would say more relevant than the identity of the metals, or as relevant, is the structure of the catalyst as a whole. So we went ahead and tested different metal POM complexes, variating the ratio between the Lewis acid metal and the POM ligands, like here the Keggin-1,2 compound or the Keggin-2,2 compound. And we also evaluate the different structure of the POM ligand, moving from the Keggin structure that is here to the Wells-Dowson variants of it, which even has two different isomers that we can evaluate, one with the vacancy here on this, let's say, internal belt, and the alpha-2 that it's removing one of these top tungsten groups from here. And what we observed for the reactivity was a very distinct profile. Usually the 2,2 was in absolute terms more performed better than the 1,2 complex. And for both the Keggin and the Wells-Dowson one. And when we got this, the alpha-2 was better than the alpha-1 Wells-Dowson isomer. And actually the zirconium alpha-2 Wells-Dowson 2,2 complex was a very sweet spot for this reaction and afforded the product without further optimization in a very nice yield. This reactivity was not limited to simple Gly-Gly, because we directly went ahead and tried other Gly-X dipeptides, so having the glycine S on the N-terminal and another amino acid on the C-terminal. And we could observe the formation of several products, so some even including heteroarenes or some polar groups, without any need for protected groups to observe this high reactivity. If we move the other way around and we use the X-Gly dipeptide, we frequently got this equivalent reactivity, showing that the catalyst can deal with in both ways. So not only the intramolecular reaction as we developed so far that helped us to get this reactivity to take off, but also the intermolecular reaction could also be observed with this catalyst. There are a few differences between forming the bond between this phenylacetic acid and benzylamine from the intramolecular reactions that I showed before, but the major trends on this catalytic activity were very similar to what I showed before. The NSO in this case was the best solvent compared to other ones, which might be probably related to a little bit better solubility of this catalyst in this system. The metal POM ratio, the 2,2 compound, as I show here again, was again a more active catalyst than the 1,2. And once again, the Wells-Dowson compound was also more active than the Keggin one. One thing that we realize here is that even though in relative terms, both of the metals presented a similar behavior, in absolute terms, the hafnium was a little bit better for the intermolecular reaction. And even though they show equivalent reactivity, we followed the work with using the hafnium catalyst, as this was a little bit better at this point. What closed the deals of this reaction and brought these moderate yields to complete conversion of the starting materials into the product was actually the concentration of the reaction, the amount of solvent that we are using. And as we decrease the amount of solvent and increase the concentration of the reaction, you can observe that the yield directly responded to it, affording nearly quantitative yields of the amide product in a little bit above 3 mole per liter concentration of the limiting reagent here, the carboxylic acid. In these high concentrations, we even have could reduce the catalyst loading from 1 to 0.25 mol% catalyst, which I think speaks of the stability of the catalyst, the activity, and how the system can be even further optimized to become more interesting from a sustainability point of view. Of course, we also tested this reaction in other substrates. It's not restricted to the model reaction that I showed before. And it still surprised me how some heteroaromatic groups can be used on this reaction without any either protective chemistry or any further drawbacks on the reaction. And all of these products can be easily isolated without having a chromatography purification. They are isolated in high purity. So I think this shows that the system can be quite useful in terms of preparative chemistry. As interesting as developing the reactivity, I think it's we should understand it. And one thing that was intriguing at the beginning, for me at least, was what would be the mechanism of this reaction if the monomeric or the dimeric species was involved. Control experiments already showed to us that this the metal-POM complex was actually the one involved in catalysis, and that the Lewis acid center was the zirconium, or the hafnium was the one doing this reaction. But if it was a dimeric or a monomeric species, this was still an open question for me, because I had conflicting scenarios in the literature about the mechanism of this reaction. On one side, I had the established work on the group in Leuven that the monomeric species would be the one to activate the dipeptide bond and expose it to the external attack of a water molecule. But on the other side, I had this recent and also very thorough mechanistic experiment talking about the activity, the mechanism of zirconium chloride amide bond formation. And they proposed that one catalytic active species could be a dinuclear compound with having the zirconiums on a configuration very similar to the zirconium POM precursor or hafnium POM precursor that I was using in these reactions. And I was honestly conflicted between these two hypotheses, because the high concentration of the reaction made me think for a while that we were having a dimeric species as the catalytic active one. Fortunately, we had started this project with phosphotungstates that has a phosphorus in this structure that can be followed through phosphorus NMR. So we could follow their behavior in solution and try to reconstruct what would be happening during the reaction. So we did a lot of control and a lot of mechanistic experiments in this to try to figure this out. I just show you the most relevant ones. First, here on the right, the kinetics that clearly show the reaction is favored by an excess of the amine, or the initial rate of the reaction is much higher than if you have an excess of carboxylic acid, makes the reaction way more sluggish than even the normal condition. So when we try to reproduce these conditions in the NMR so that we could figure out what was going around in solution, we got this, I would argue, a very clear picture of what could be happening. So here we have just the catalyst in solution in the same concentrations that we had in a reaction, and a couple of control experiments confirmed that this was mostly the dimeric species. And then when we add different substrates to this to see which effect these substrates would have in the solution chemistry of this POM, we found out a very distinct behavior or influence from these two reagents. While the benzylamine would afford mainly the monomeric species on this in solution, the carboxylic acid for the complete different one, which I still rationalize that is the dimeric one, but if not exactly this, at least a monomeric species that is fully saturated by carboxylic acids, making this much less reactive. Maybe some off-cycle species that would withdraw the catalyst from its actual catalytic cycle. But more interesting than that, I think, is that when we start adding amine to this third solution here, this system reverts back to something that is very similar to what we observed when only amine was present. And for us, making a strong case that the monomeric species would be the one responsible for the catalytic activity observed. And this would be actually very consistent with everything else that we knew from the hydrolysis work. So everything fell into place quite nicely with after these experiments. So even though we haven't really looked into the elementary steps of this catalytic cycle to figure out other features, such as if the amine attacks the carboxylic acid through an inner or an outer sphere mechanism. Now we are, I would say, quite convinced that the monomeric Zr-POM or hafnium-POM species is the active one. In fact, recently we have also shown that if you modulate this equilibrium by changing the dielectric constant of the reaction, decreasing it, you favor the dissociation of the metal-POM complex to the monomeric species, and that this dissociation improves the yield, thus confirming that it's actually the monomeric species that most likely is the catalytically active one. I think as interesting as the mechanism is one aspect that you might have realized so far, that our reactions don't have any water scavenger of any sort. And since the beginning, we have seen that molecular sieves wasn't doing much. So we just, at some point, we just drop it. I mean, what would be the point of using if it's not giving any benefits of any kind? The question is why that is happening. And that's something that we are still looking into understand it better from the molecular perspective. But we started investigating this by showing that this water tolerance, or there's no need of the water scavenging, was real by running this reaction in strictly anhydrous conditions and then adding control amounts of water. And this is the sort of things that we observed. You could add up to twice as much water as the reaction would produce on its own, and still would observe very high yields for this reaction, which is quite interesting compared to other amide bond formation reactions that are out there. More importantly, when we look into the kinetics, it just revealed that more water you add, slower the reaction gets, just showing that this is probably about the thermodynamically equilibrium evolving on having or not having water in the reaction, but not exactly decomposing the catalyst as it has been observed for other species in the literature. I think this, to make this more concrete, it's also interesting to put this into perspective with other catalysts that have been reported in the literature. To be honest, in a little bit of a dishonest way, because probably these other researchers were not as concerned about this aspect as we are. But as you can see, concerning the water removal from the reactions and the recyclability, our catalyst is one of the few that check both boxes here and provided, let's say, a very good potential on eliminating these waste generators that have to be involved on the amide bond formation. In fact, we observed the recyclability of our system having 3 perfect reactions afterward. And as you see from the phosphorus NMR down here on the bottom right, We could even go further than the third cycle, because after the third reaction, we still got an intact catalyst on the could be recovered from the reaction. Most likely would be still active on it, but the concept was proved, so we just stopped it at three reactions. And I think this makes a very nice picture for us to look also on other metal-oxo clusters that have been used for the hydrolysis work, if they would present equivalent or an even better reactivity profile. And this brings me to the last part of my of the work I want to talk about it today, with a little bit of our work using zirconium MOFs to enable to develop the same reactivity forming the amide bonds. And the reason why we do that is because the same profile that was observed a couple of years ago with zirconium POMs was also observed with zirconium MOFs, with this cyclized dipeptide being formed in the early stages of the reaction and then being fully hydrolyzed at the end. But you can see here on the time scale that actually the MOFs present a much better, much more promising or faster reactivity, that if we could get this on the amide bond formation side, this would be as interesting as getting the metal POM complexes as we did. So of course, I won't bother you with the many details on our work, but just to say that this chemistry works also very well. And using UIO66 structure, the zirconium MOF, we can observe nearly quantitative yields of the cyclized dipeptide again, with no interference of any hydrolysis has been observed. And also, again, no special reaction conditions, dry solvents or drying agents are necessary for observing this sort of yield. It's also cool here that actually what worked quite nicely for our reaction is the alcoholic solvents instead of the tricky DNSO solvent that we have used before. And this is very cool because this green bio-based solvent is not so common on catalytic amide bond formations. And in our case, it allowed us to move one step ahead from the zirconium POM catalyst that we had before, because we could isolate all these products in quite nice purity just by centrifuging the reaction and evaporating the supernatant. And as I show here, in comparison with the previous zirconium POM catalyst, the MOFs can provide a very similar, sometimes even a little bit better reactivity. And there is also some equivalence on using the Gly-X or the X-Gly dipeptides. Similar to what we observed at the zirconium POMs, but I would say even more promising would be the robustness of this zirconium UIO66 MOF that we use it for catalysts. Of course, this is very typical from heterogeneous materials like MOFs, that you can get a nice recyclability, but this works very well for our reaction over 5 cycles here. We were able to test. But what threw me off here is actually the water tolerance that the system presents, that is much, much higher than what we observed for the zirconium POMs. In terms of molar excess of water, this is around 10 to 15 times higher than what we observed now. Even when we've got 70% of the water inside of the reaction, we still can get more than 80% of the cyclized product in this case. And I don't think there are many systems out there that can do this, making, I think, the Metal-Oxo cluster catalyst is very, with an immense potential that we still have to understand and explore very carefully. With this, I conclude the chemistry part of my talk. I hope I can convince you that there's a big potential on Metal-Oxo clusters, regardless if you go for the different kind of clusters that I have shown before. And hopefully by further understanding and tuning the fundamental aspects of this system, we'll be able to get even better amide bond formation reactions. And hopefully in the near future, also other reactions will be benefited by the catalytic properties of these compounds. Of course, I cannot finish without thanking all the people that helped me to get through here and be considered for this award. The people that helped me before my time in Belgium, I mean, of course, probably some names are missing here, but I think most of the people that work directly with me is acknowledged here. Of course, I'm very grateful for the funding agents that paid all the bills for me to enjoy the science in the lab before my time in Belgium, here on the right, but also the funding I've been receiving here in Belgium. And at last, I pay my tribute again to the team in Leuven, which I listed here, those that are directly involved in the projects that I've been talking about. But all of them are deeply acknowledged by all their help and dedication on making my time here in Belgium much better. With that, I thank you all for your kind attention, and I'm happy to take any questions. Thank you.
Thank you. Do you hear me?
Yes.
Okay. So in the question and answer session, I see no questions. But I have one or two questions. The first one is the structure of the polyoxymetallate dependent on the solvent? If you go from water to DMSO or methanol or whatsoever, you have a different structure of the catalyst.
Of the catalyst depending on the solvent?
There's no difference in structure whether you go working in water or whether you work in DMSO?
No. I think that's one of the nicest features of these compounds. They are very robust, very stable. So you can almost do whatever you want with them, and they are still there being catalytic active.
Mm-hmm. How do you separate the catalyst from the products?
So they are anionic compounds, right? So they always have a cation that is coupled to them. And actually, when we work in organic solvents like the DMSO that I've shown, it's very easy to precipitate them by adding, let's say, a less polar solvent. In this case, I quench the reaction with simple DCM or ethyl acetate, and they precipitate. You can just centrifuge, wash a little bit, and then you can use again directly.
Okay, thank you.
There is one question in the chat, so I will take that one. Which discrete cluster did you use, and did you use them also for catalyzing the same reactions?
The discrete oxo clusters that I used that I mentioned at the beginning, we are still, I would say, the first steps of this work. We have been first, mimicking the reactivity we have observed with MOFs, using mainly the versions of the zirconium-6 cluster that have been reported. But there are a couple of different things there on working with the amide bond format that we are still trying to understand how to, I would say, better rationalize them and use them in a more productive way.
Another question for me is, when you use metal-organic frameworks, these are micropores.
Yes.
Are the reactions really occurring in these micropores or at the external surface of your catalyst particles? What do you think?
Oh, well, that's certainly a great question and a great matter of debate in our group, in Leuven as a whole. For this case, I think we have been comparing the size of the pores that we have on the UIO66 and the substrate that we have. We might have a chance to get the substrate inside, but I mean, my personal feeling is that this is still happening. There's a lot of contribution on the outer surface of it, instead of some special pore effect or confined systems.
Yeah. Okay. So the questions and answers. I have a couple of questions. One of these, out of the many positive properties of these metal-oxo catalysts, such as POMs, what do you think is the key advantage that separates them from direct competitors?
Well, that's a very broad question. Well, what I like them, it's not that I think they will beat the competition right away, but I think we certainly need to understand them better. There is no structure-activity relationship studies out there that show us the different compositions or the different metal ratios or the different cations or any sort of structural characteristic relating this to other catalysts. But if we got to understand this and use them in a productive way, I think that the fact that they are very stable and they can be easily separated from the reaction mixtures might be an advantage on producing more, let's say, sustainable, for a very general term, sustainable catalytic systems that can be reused over time, several times, and then, well, reduce a little bit the waste generation that we have with other catalytic systems.
Okay, thank you. Another question here is, can you briefly describe the preparation of these catalysts and comment on the yield? And is it challenging to separate the different types of, like, alpha 1, alpha 2, Dawson 1, 1, 2?
No, not really. Actually, the methods for the more established POMs, they are very, I would say, very well studied, and you can get quite selectively to each of the structures that I have shown on that slide. In terms of the yield or the efficiency, it also varies on how good your process is and how easy it is for the POM to form and or precipitate. But I usually get yields between 50 and 70% on the synthesis of the final compound. The one that I already used for them.
Yeah, okay. The last question which came in is it known what the influence of the POM itself has on the mechanism of the reaction? And why is this polyoxometallate more beneficial than any other anion bonded to hafnium or zirconium?
Well, the short answer for that is no. The effect of the polyoxometallate ligand could range from simply holding the metal there in place, but working with these reactions, I have the feeling that we will still understand better what this oxygen shell that we have around the POM will have an effect on the reaction, because there's some basicity there that might be contributing for the formation of the amide bonds that we are observing. But for giving a precise reason at this moment, I don't think we have the results to speculate that further.
Okay, thank you. I think these are the questions here. I propose that we close the session. I congratulate you with your prize, and I hope to meet you in the near future. Thank you.
Thank you.